This is a revision video for AQA GCSE Chemistry or Combined Science, Unit 6, the rate and extent of chemical change, which is all about how we can speed up chemical reactions or how, if it's a reversible reaction, we can change the amount of product that's being made. 40% of the marks in GCSE Science exams are for being able to recall the facts that are listed in the specification. So this is a summary video to allow you to check for yourself whether you do actually know those facts. Once you know them all, then you can move on to making sure that you can apply them or use them to analyse data. The rate of a chemical reaction is its speed, how fast it's going. In order to understand rates of reaction, we need to understand collision theory, the idea that in order for a chemical reaction to take place, particles need to collide, so they need to bang into each other, and they need to have a minimum amount of energy called the activation energy, and that will be different for every chemical reaction. So activation energy is the minimum amount of energy that particles need to react. An energy profile is a kind of diagram that we draw to show a chemical reaction proceeding. So for an exothermic reaction, it's going to look like this. We've got a line representing reactants, a line representing products, and in between them there's this kind of hump. Whether a reaction is exothermic or endothermic, you're going to have this hump. The line is going to go up first, and this is because every chemical reaction needs to take in a little bit of energy before it starts. That's the activation energy, and that energy is going to be used to break bonds. So the activation energy in this diagram is represented by the pink arrow, and the overall energy change is represented by the blue arrow. And I can tell that this is an exothermic energy profile because the products have less energy than the reactants do. And if you remember, the amount of energy in total has to be conserved. So if the products have less energy than the reactants, that difference, that energy must have been given out, and so actually it's been used to heat up the surroundings, which is what we understand by an exothermic reaction. The two formulae listed in the specification for calculating mean rate of reaction are rate of reaction is amount of reactant used divided by time, and rate of reaction is amount of product formed divided by time. There are lots of different units that you could use for rate of reaction, but the ones listed in the specification are grams per second or centimetres cubed per second. You could have a mass or a volume with slightly different units, say kilograms or decimeters cubed, and you could have a time that's different, like minutes or hours, but it's always going to be either a mass or a volume divided by a time. So in order to calculate a mean rate, we either need a mass or a volume change, and we need a time. Now, if we've got a graph, we would look at that graph, and the gradient or the steepness represents the rate. So where the graph is steepest, that's where the reaction is happening fastest. I would calculate the gradient by using the change in mass divided by the change in time. And if the graph was curved, what I would need to do is draw a tangent for the point and then use that to calculate a rate. So let's look at an example. Here I've got a smooth curved line. And so if I wanted to know what the rate was at a particular point, then I draw a straight line that meets the curve just at that point, like this. That's what we call a tangent. And you want to make your tangent as long as possible because that's going to lead you to be as accurate as possible. And then I can use that line to work out the gradient. So here, my line's going up from 2 grams per 9 grams, so that's a change of 7, and that's taken 10 seconds to happen. So 7 grams divided by 10 seconds gives me a rate of 0.7 grams per second. And you could be either asked to describe that process about how you draw a tangent, or you could be asked to actually do it. There are 5 factors that you can change to alter the rate of a reaction: pressure, surface area, concentration, catalyst, and temperature. I remember this by telling a little life story. So you started off, you first went to primary school, so PR for primary, but also PR for pressure. Then you went to secondary school, so secondary, surface area, both start with S. Then next year, you're maybe going to go to college, CO for concentration. After that, you go on and have a career, CA for catalyst. And after all of that, you're very tired, so T for temperature. To increase the surface area of a substance, you're going to break it up into smaller pieces or maybe grind it into a powder. If you have a cube and you cut each side of that cube into 2, so you cut the length in 2, you cut the width in 2, and you cut the height in 2, you will double the surface area, a bit like this. That's also true if you cut each side into 3, you will triple the surface area, and if you cut each side into 10, you will multiply the surface area by 10, but the volume will stay the same. As we increase the surface area, that will increase the rate of reaction. This is because increasing the surface area is going to increase the number of collisions that can happen in a second. So we say the particles collide more frequently or more often. It's really important that you've got that idea that there are more collisions happening in 1 second, not just more collisions in general. To calculate the surface area to volume ratio, we obviously need the surface area and the volume. So if you think about a cube, it has 6 sides, and then the edges of each of those sides are going to be the same length because it's a cube. So to work out the surface area, we're going to work out the area of one side, so the length times the length, or the length squared, and then multiply that by 6. And then to work out the volume of a cube, you take that length and you cube it. So then we can work out the surface area to volume ratio by putting them together in a ratio or just dividing the surface area by the volume. As we increase concentration, we're going to increase the rate of reaction. And this is going to happen because we've got more particles in the same volume, and so again, this is going to lead them to collide more frequently. As you increase the temperature, you'll also increase the rate of reaction, and this is for 2 reasons. Partly, it's that as you increase temperature, you're giving the particles more energy, so they move faster, and they're more likely to collide more frequently. But also, it's because it's more likely that one individual particle will have the activation energy. So more of the collisions that do happen are successful. A catalyst is a chemical that speeds up the rate of reaction without being used up itself. And it does this by providing an alternative reaction pathway that has a lower activation energy. So this is a bit like providing a shortcut, which takes less energy to do. So we drew this energy profile earlier, and you can see the green line represents what happens with a catalyst. So the reaction starts with the same amount of energy and ends with the same amount of energy, but in between, the activation energy is lower. So it's more likely that a particle that's reacting when it's near to a catalyst will be able to have a successful collision and therefore be able to react. Using a catalyst saves money because the other ways of speeding up a reaction, like heating it up, are much more expensive because they're going to use a lot of energy. A precipitate is a solid that forms from a mixture of liquids, and you can tell if a reaction makes a precipitate because the liquid will go cloudy. So the classic example of this is you've probably done this practical where you mixed dilute sodium thiosulfate with dilute hydrochloric acid, and after a little while it produces a sulfur precipitate, which is a sort of yellow solid, and it makes the solution go cloudy, and you might have done this on top of a cross and seen the cross disappear. Turbidity is just another name for cloudiness, so if an exam question asks you to describe how you would use turbidity to show how the rate of reaction was affected, say, by concentration, what they're asking you to do is describe that experiment with the disappearing cross. Describe an experiment where a precipitate is formed and it goes cloudy, and then you measure how long it takes to go cloudy. You could either measure this by watching for a cross to disappear, as we've done just there, but also you could use a light sensor, or it's sometimes called a colorimeter, a sort of a piece of equipment that shines a beam of light through a sample and basically measures how much light is being absorbed and will give you a definitive point where where no more light is going through the reaction. A reaction that produces a gas will produce bubbles. And collecting gas over water, you've probably also done in your science lessons. So this is a process where you're going to use a bung and a delivery tube to collect the gas that's being produced in usually a conical flask, but maybe sometimes a boiling tube as well. And then you have a big bowl of water, and inside that is going to be a measuring cylinder. So the measuring cylinder is full of water, and then you put the delivery tube from your reaction into that measuring cylinder. So the gas that's being produced is going to push the water out of the measuring cylinder and allow you to measure how much gas has been produced. You could also measure this using a gas syringe. A reversible reaction is a reaction in which the products can react together to form back into the reactants, and it's shown using this double-headed arrow. If the forward reaction is exothermic, then the backward reaction must be endothermic, and if the forward reaction is endothermic, then the backward reaction must be exothermic. This is because we know that breaking bonds takes in energy, and making bonds releases energy. And in a reversible reaction, we've got the same bonds being made and broken. It's just that the ones that are broken in the forward reaction are made in the reverse reaction and vice versa. Equilibrium happens when the forward and backward reactions are occurring at the same rate in a closed system, and this means that the concentration of the reactants and the products will be unchanging. A closed system is just where we have a reaction vessel where it's sealed and no energy and no matter, so no atoms, can get in or out. This last part is just for higher tier, so if you're sitting the foundation tier, you don't need to watch it. If we add a reactant, then the position of equilibrium is going to shift to the right. And this is because the forward reaction is going to be favoured. If you think about it, if we're adding more of the reactants, the things that are on the left, we're increasing the concentration of them. They're more likely to collide with the other chemicals and they're more likely to react. Meanwhile, the backward reaction is still going at the same speed. So overall, this is going to push the equilibrium to the right. If we add a product, then the reverse happens. So the equilibrium shifts to the left, and this is happening because the backward reaction is going to be favoured, or the reverse reaction. If we increase the temperature, then we need to know which reaction is exothermic and which reaction is endothermic. Le Chatelier's principle tells us that whatever we try to do to a system that's at equilibrium, the system will try to resist it. It will try to counteract that change. So if we heat a reaction up, it will try to cool itself down. And the way that that happens is that the endothermic reaction will be favoured. So the equilibrium will move to the side that is produced by whichever reaction is endothermic. If we increase the pressure, again, Le Chatelier's principle tells us that the system will shift to try and counteract the change. And so if we've increased the pressure, it's going to do whichever reaction decreases the pressure. And we can work this out by looking at the chemical formulae and seeing which of the two sides of the equation has fewer gas molecules on it. So if we increase the pressure, the equilibrium will shift to the side that has fewest gas molecules. If we add a catalyst, this isn't actually going to affect the position of the equilibrium. And the reason for that is that it will speed up the forward reaction and the backward reaction by the same amount. I hope that was helpful. Don't forget to subscribe.